This is a recast of the 6,600-word piece, Recursive Neural Networks, RNN, from Schneepat.com. This article discusses recursive neural networks, RNNs, and their applications in various fields such as natural language processing, sentiment analysis, language translation, text classification, image processing, video analysis, and object recognition. It highlights the ability of RNNs to capture hierarchical structures, process sequential data, and handle variable length input sequences effectively. The article also mentions the challenges faced by RNNs, such as the vanishing gradient problem and computational complexity, and the ongoing research to overcome these limitations. Let's listen in.
Today, we're diving into the world of recursive neural networks, RNNs. These networks are a type of artificial neural network used in machine learning to process structured data, such as natural language sentences or parse trees.
That's right. Unlike traditional feed-forward neural networks that process data sequentially, RNNs can recursively evaluate the representations of the entire structure they are fed. This means they can capture complex relationships and dependencies between different parts of the input.
Absolutely. And the concept of recursive neural networks is actually inspired by our own human ability to understand and produce recursive structures in language. By applying the same computations to different parts of the input, RNNs can model the hierarchical relationships and produce high-level representations of the data.
It's fascinating how these networks can handle structured data like trees or graphs. Traditional neural networks can't effectively process this type of variable-sized input, which is where RNNs come in. They recursively apply the same neural network weights to substructures of the input, allowing them to capture the compositional structure.
That's a great point. The ability of RNNs to effectively process structured data is particularly useful in natural language processing tasks. In tasks like language modeling or sentiment analysis, where the meaning of a sentence depends on its constituent words and phrases, RNNs can exploit the recursive nature of the data to build a hierarchical representation.
Exactly. And not only can RNNs effectively model the compositional structure, but they can also handle sequences of variable length. This makes them applicable to a wide range of tasks like language modeling, sentiment analysis, and machine translation.
Right. The recursive nature of RNNs allows them to adapt to different lengths of sequences, making them quite versatile in natural language processing applications.
Now let's talk about how these networks are trained. The process involves calculating gradients with respect to the weights of the network. These gradients are then used to update the weights through an optimization algorithm like stochastic gradient descent.
Yes, but calculating gradients in RNNs can be challenging due to their recursive nature. One approach to address this challenge is through backpropagation through structure, BPTS. BPTS applies the chain rule of calculus to propagate gradients through the recursive structure of the RNN.
Another approach is truncated backpropagation through time, TBPTT. This approach restricts the length of sequences over which gradients are propagated. This helps mitigate the issue of exploding or vanishing gradients, which can occur when dealing with recurrent connections.
Understanding the training process of RNNs and the challenges associated with it is crucial for effectively using them in various applications. These networks have shown great potential in tasks like natural language processing, where structured data plays a key role.
Absolutely. RNNs allow us to capture the complexity of language and model it effectively. They have opened up new possibilities in understanding and processing natural language data.
And that wraps up our discussion for today. We hope you found it informative and got a better understanding of recursive neural networks and their applications in natural language processing.
Stay tuned for our next episode, where we'll be diving deeper into the architecture, training algorithms, and applications of recursive neural networks.
In today's episode, we're going to talk about recursive neural networks, also known as RNNs, and their ability to capture hierarchical structures in input data.
That's right, RNNs are unique because they can capture dependencies at different levels of abstraction. They do this by applying the same neural network model recursively over a tree-like structure that represents the data.
This structure consists of nodes and edges. Nodes represent different information units, like words or phrases, while edges represent the relationships between these units.
Exactly. At each node, the deep learning model not only considers the current node's features, but also takes into account the information from its child nodes or leaf units.
This allows RNNs to generate meaningful representations for complex, contextual information. It's especially useful for tasks where history matters, like natural language processing and speech recognition. LSTMs and GRUs incorporate gating mechanisms that allow for more efficient learning and better preservation of long-term dependencies in sequential data.
Exactly. And recent studies have explored the application of RNNs in various domains, including natural language processing, computer vision, and speech recognition. This shows their versatility and potential for solving a wide range of problems.
Looking ahead, future research directions for RNNs include exploring more advanced architectures, investigating optimal hyperparameter configurations, and devising novel training algorithms to further improve their performance and scalability.
Absolutely. The recent developments in RNNs have opened up exciting new possibilities, making them an increasingly important tool in the field of deep learning.
And one crucial development in the field of RNNs is the introduction of long short-term memory, LSTM units. LSTMs aim to overcome the limitations of traditional RNNs when dealing with long sequences.
LSTMs incorporate memory cells that can store and access information over long periods. This allows the network to retain important context and alleviate the vanishing gradient problem.
Right. These memory cells are equipped with forget, input, and output gates, which control the flow of information in and out of the cells. This gating mechanism enables LSTMs to selectively retain or discard information based on its significance, improving their ability to capture long-term dependencies.
LSTMs have emerged as a powerful and widely used tool in various applications, including speech recognition, natural language processing, and time series analysis.
Moving on, state-of-the-art models using RNNs have shown remarkable success across various domains.
One such model is the long short-term memory, LSTM, which addresses the vanishing gradient problem. LSTMs have achieved state-of-the-art results in tasks such as language modeling, text classification, sentiment analysis, and machine translation.
LSTMs have also proven effective in speech recognition tasks, achieving competitive results in automated speech recognition and phoneme classification.
Another noteworthy model is the gated recurrent unit, GRU, which operates similarly to LSTM and has demonstrated comparable performance in various tasks.
Overall, state-of-the-art models using RNNs, such as LSTMs and GRUs, provide robust solutions to a wide range of sequential and temporal problems.
And this highlights the potential of these networks in advancing the field of machine learning and artificial intelligence.
Absolutely. One potential advancement mentioned in the article is the development of more sophisticated architectures for RNNs. These architectures would be able to handle more complex data structures, such as multiple nested levels of recursion. This means that RNNs would be able to process even more diverse types of data, like natural language expressions, with complex syntactic structures or hierarchical time series data.
That's right. And with advancements in hardware and computational power, RNNs can be deployed on edge devices, like smartphones or IoT devices. This would enable real-time processing of data without the need for constant connectivity to the cloud. Imagine being able to use your smartphone for various tasks like language translation or speech recognition without relying on an internet connection.
And it doesn't stop there. RNNs can also be combined with other types of neural networks, such as convolutional neural networks, CNNs, or generative adversarial networks, GANs. These hybrid models can achieve better performance on tasks like image recognition or natural language processing.
Exactly. The combination of different neural network architectures allows for a more comprehensive approach to solving complex problems. This could lead to significant advancements in fields like healthcare, finance, natural language processing, and robotics.
Absolutely. RNNs have already revolutionized various domains, but with continuous research and development, their potential impact will only continue to grow.
That's right. RNNs are specifically designed to process structured data, such as sequences or trees. Unlike traditional feed-forward neural networks, RNNs have a cyclical connection structure that allows them to capture the temporal dependencies present in sequential or hierarchical data.
And this makes them particularly well-suited for tasks like natural language processing, where the order of words in a sentence or the hierarchical structure of words in a parsed tree is crucial for understanding meaning.
RNNs achieve this by recursively applying the same set of weights to each node in the input, generating a hidden state vector that encodes the relevant information. This hidden state is then used to make predictions or perform further processing steps.
It's truly fascinating how RNNs offer a powerful solution for modeling and analyzing structured data. They have enabled breakthroughs in areas such as machine translation, sentiment analysis, and speech recognition.
Absolutely. But it's important to note that RNNs also have their own limitations, such as difficulties in capturing long-term dependencies and vanishing exploding gradient problems.
That's where variants like long short-term memory, LSTM, and gated recurrent units, GRU, come into play. These modifications address the vanishing gradient problem and improve the performance of RNNs in capturing long-term dependencies.
Right. And recent advancements in the field have led to the development of more sophisticated models, like tree LSTMs and n-ary RNNs. These models offer enhanced capabilities for capturing structural information in data.
It's amazing to see how RNNs continue to evolve and address their limitations. As a result, they are finding applications in various domains and contributing to advancements in natural language understanding and generation, as well as other fields involving sequential and structured data processing.
Absolutely. The potential impact of RNNs in various fields cannot be overstated. In natural language processing, RNNs can capture hierarchical structures and dependencies, enabling them to effectively model and analyze complex linguistic patterns like syntax, semantics, and sentiment analysis.
And in image processing, RNNs have been successful in capturing the spatial relationships between different parts of an image. This enables tasks like image captioning and object recognition.
RNNs have also shown promising results in fields like speech recognition, recommendation systems, and bioinformatics. Their ability to handle variable-length sequences and learn complex dependencies make them a valuable tool for problems involving sequential data.
Exactly. As the potential applications of RNNs continue to expand, their importance is increasingly recognized. This offers exciting opportunities for advancements in various fields.
And that's why further research and exploration of RNNs is encouraged. There are still areas that need addressing and extending. For example, there is a need for more research focused on developing efficient and scalable algorithms for training RNNs on large datasets.
Absolutely, and further investigation into the use of RNNs in complex domains, such as natural language understanding and computer vision, could lead to even more advancements.
Exploring new architectures and variations of RNNs, like gated RNNs and LSTMs, could also improve their overall performance and capabilities.
And let's not forget about the potential of combining RNNs with other machine learning techniques like deep learning, reinforcement learning, and unsupervised learning. This could open up new avenues for improving the performance of RNNs.
With these future directions in mind, researchers have an exciting opportunity to continue pushing the boundaries of RNNs and unlocking their full potential. Now, let's talk about the key differences between RNNs and traditional feed-forward neural networks.
One major difference is that RNNs can process sequences of input data, while traditional neural networks process each input independently.
That's right. RNNs can store information from previous inputs, which enables them to capture important temporal dependencies in sequential data. This is possible because of recurrent connections within the network.
These recurrent connections create a feedback loop where the output of the previous time step is fed back as an input to the current time step. This gives RNNs memory and allows them to learn and process time-dependent patterns.
On the other hand, traditional neural networks lack this recurrent feedback mechanism, so they can't effectively model and capture sequential information.
That's why RNNs excel in tasks that involve language understanding and generation. They can implicitly learn syntactic and semantic relationships because of their ability to capture dependencies at multiple levels of the linguistic hierarchy.
This recursive structure allows RNNs to generate coherent and context-aware sentences, making them well-suited for applications like language translation, sentiment analysis, and speech recognition.
Absolutely. And as the field of deep learning continues to advance, we can expect further research and innovations to enhance the capabilities of RNNs in natural language processing.
Now, let's talk about the applications of recursive neural networks.
RNNs have gained popularity in various domains, with one significant application area being natural language processing, or NLP.
That's right. RNNs have been used for tasks like sentiment analysis, text classification, and machine translation in NLP.
They've also made advancements in computer vision, particularly in image captioning and scene understanding. By modeling hierarchical relationships, RNNs can capture the structural information present in these tasks.
In addition, RNNs have shown promise in speech recognition and audio processing. Their ability to handle sequential data and capture dependencies between audio segments has improved automatic speech recognition systems.
Overall, the versatility of RNNs has opened up opportunities for their usage in a wide range of applications, making them a valuable tool in machine learning and artificial intelligence.
Lastly, let's talk specifically about NLP and how RNNs have revolutionized the field.
RNNs address the limitations of traditional models by capturing the structural dependencies within sentences and considering the context of each word.
That's right. They recursively apply the same weight matrices to construct a hierarchical representation of the input sentence, allowing information to flow from lower-level features to higher-level representations.
This enables RNNs to effectively model complex linguistic structures and capture long-range dependencies. The incorporation of word embeddings has also contributed to their success in language understanding tasks.
However, RNNs still face challenges such as computational complexity and handling out-of-vocabulary words. These challenges motivate further research and development in the NLP field.
And that wraps up our discussion for today. We hope you found it informative and got a better understanding of recursive neural networks and their applications in natural language processing.
Stay tuned for our next episode, where we'll be diving deeper into the architecture, training algorithms, and applications of recursive neural networks.
Thanks for listening. In today's episode, we're going to talk about sentiment analysis and how recursive neural networks, or RNNs, have become an essential tool for understanding public opinion on various topics.
That's right. Sentiment analysis is the process of determining and categorizing the sentiment expressed in a text, such as positive, negative, or neutral. With the increasing amount of online user-generated content, sentiment analysis has become more important than ever.
And RNNs have gained attention in recent years for their ability to capture the hierarchical structure of language, which is crucial for sentiment analysis. By recursively combining the representations of smaller phrases and words, RNNs can model the sentiment expressed in larger chunks of text.
This hierarchical approach allows RNNs to capture contextual information and dependencies that contribute to the overall sentiment of a text, making them effective models for sentiment analysis tasks.
Moving on to language translation, RNNs have found numerous applications in this field as well. Traditional machine translation systems rely on statistical models that make translation decisions based on the frequency or occurrence of words or phrases, but they often fail to capture the semantic and syntactic structure of sentences, resulting in poor quality translations.
However, RNNs have the ability to capture the hierarchical structure of natural language sentences and can generate more coherent and accurate translations. By using recursive neural networks, researchers have been able to improve the performance of machine translation systems, leading to more effective and reliable language translation.
Another area where RNNs are proving to be valuable is text classification. Text classification refers to categorizing textual data into predefined classes or categories. With the exponential growth of information available in the digital world, efficient text classification algorithms are needed.
RNNs employ a hierarchical structure that captures syntactic dependencies within the text, allowing them to better model the relationships between words. By recursively applying a neural network to input sequences, RNNs can extract meaningful features and classify text accurately. This approach has shown promising results in various domains, including sentiment analysis, spam filtering, and topic modeling.
However, RNNs do come with challenges such as computational overhead and the risk of overfitting. Ongoing research is being conducted to explore and refine the use of RNNs for text classification tasks.
When it comes to image processing, RNNs have proven to be effective as well. Image processing involves manipulating digital images to enhance their quality or extract relevant information. RNNs are particularly useful for tasks like image captioning, where the goal is to generate a descriptive text based on an input image.
The recursive structure of RNNs allows them to capture the dependencies between different regions within an image, enabling them to better understand the context and generate accurate captions. RNNs can also be used for tasks like image synthesis, in painting, and style transfer, where the goal is to generate visually appealing images.
And in the realm of computer vision, object recognition is a crucial task in various applications such as image classification, robotics, and autonomous vehicles. Traditional approaches to object recognition often rely on handcrafted features, which can be limited in their ability to capture complex visual patterns.
However, with the advent of deep learning and RNNs, machines can now learn hierarchical representations directly from raw input data. RNNs have shown remarkable performance in object recognition tasks due to their ability to process sequential information and capture long-term dependencies.
By recursively combining local feature representations to form a global understanding, RNNs can effectively capture spatial, temporal, and semantic dependencies within images. This leads to improved object detection and classification accuracy, making RNN-based approaches prevalent in the field of computer vision.
And there you have it, the main points of the article. RNNs are proving to be invaluable in sentiment analysis, language translation, text classification, image processing, and object recognition.
Absolutely. Stay tuned for our next episode, where we'll be diving deeper into the architecture, training algorithms, and applications of recursive neural networks.
Thanks for listening.
Today, we're going to talk about recursive neural networks, RNNs, and their applications in image captioning and video analysis. RNNs are a type of neural network that can handle sequential data, making them suitable for tasks like image captioning and video analysis.
That's right. The basic idea behind using RNNs for image captioning is to generate a sequence of words that describe the content of an image. The input to the network is the image, which is transformed into a feature vector using a pre-trained convolutional neural network. This feature vector is then fed into the RNN, which generates a sequence of words based on the input image.
And the use of RNNs in image captioning has shown promising results. The generated captions are more accurate and meaningful compared to other traditional methods. However, there are still challenges to overcome, such as handling long dependencies and generating captions that are both accurate and fluent.
Moving on to video analysis, RNNs can also be used to analyze and interpret the content of video data. One common task in video analysis is action recognition, which aims to classify and identify specific actions or activities in a video.
That's right. By analyzing the sequential information in video frames, RNNs can learn to recognize actions and activities based on patterns and movement observed over time. This has applications in various fields, such as surveillance, sports analysis, human-computer interaction, and robotics.
Definitely. The use of RNNs in video analysis has shown promising results in advancing the field of computer vision.
In conclusion, RNNs have proven to be highly effective in dealing with structured data like natural language sentences or trees. They can capture compositional structure by recursively applying a set of predetermined operations, allowing them to capture long-range dependencies and contextual information effectively.
However, RNNs still face some challenges. For instance, they suffer from the vanishing gradient problem, which affects their ability to learn long-term dependencies. But researchers have proposed improvements to address these limitations, such as gating mechanisms like long short-term memory, LSTM, and gated recurrent unit, GRU.
That's right. These advancements have greatly enhanced the performance of RNNs, making them a promising tool for various tasks in natural language processing.
In addition to their advantages, RNNs also encounter challenges. One major challenge is the computational complexity associated with training and inference of RNNs, especially for large-scale problems.
Absolutely. Despite these challenges, RNNs continue to be an active area of research and hold promise for advancing various applications in machine learning and artificial intelligence.
One significant advantage of RNNs is their ability to capture hierarchical structures in data, making them particularly useful for tasks such as parsing, sentiment analysis, and natural language processing.
And unlike traditional feed-forward neural networks, RNNs can handle variable length input sequences effectively. This flexibility allows them to process data with different lengths.
That's right. Another advantage of RNNs over other models is their ability to capture both local and global context information by recursively applying the same set of parameters to each substructure of the input data.
And they can dynamically incorporate both past and current information while processing sequences, making them particularly useful for tasks like language modeling, speech recognition, and sentiment analysis.
Absolutely. And RNNs can also learn representations that capture long-term dependencies and temporal patterns, which makes them excel in time series prediction and forecasting tasks.
The flexibility of RNNs to process various data types and their capacity to model sequential information make them a powerful tool in numerous application domains.
That's right. They're particularly effective in tasks that involve handling sequential and hierarchical data, such as natural language processing and image recognition.
RNNs have a recursive architecture that allows them to handle hierarchical data by applying the same set of parameters at different levels of abstraction. This recursive processing enables them to capture the relationships and structure inherent in the data.
And this ability to recursively process and analyze data gives RNNs a significant advantage over conventional feed-forward neural networks when dealing with sequential and hierarchical data.
Absolutely. RNNs have proven to be highly effective in tasks that require contextual understanding. They excel at capturing long-range dependencies in data, which allows them to effectively model the hierarchical structure found in natural language.
And that contextual understanding is crucial in tasks like sentiment analysis or machine translation. By processing sentences recursively, RNNs can capture intricate relationships between words, phrases, and sentences, leading to more accurate predictions and classifications.
RNNs have also shown success in domains like computer vision and speech recognition, demonstrating their versatility and effectiveness in capturing contextual information in different types of data.
However, it's important to note that RNNs do have some challenges and limitations. One of the prominent challenges is the vanishing or exploding gradient problem.
Yes, the vanishing gradient problem occurs when gradients exponentially decrease as they propagate through time or layers, hindering the learning process. And the exploding gradient problem occurs when gradients exponentially increase, leading to unstable training.
These issues make it challenging for RNNs to effectively learn dependencies over long sequences. But there are techniques like gradient clipping and gradient normalization that can help mitigate these problems.
Another limitation of RNNs is their difficulty in capturing long-term dependencies. Traditional neural networks struggle to retain information from previous time steps, which hampers their ability to discern sequential patterns and dependencies.
That's where RNNs shine. They can retain and accumulate information from previous time steps, allowing them to capture long-term dependencies effectively.
And this makes RNNs invaluable in various applications that rely on sequential information processing, like natural language processing and speech recognition.
Absolutely. Despite these challenges and limitations, RNNs continue to be extensively studied and widely applied in various fields that require the analysis of sequential and hierarchical data.
And researchers are constantly working on enhancing RNN architecture, training algorithms, and performance optimization techniques to overcome these challenges.
That's right. One major limitation of RNNs is their computationally expensive training process. Since RNNs process one input at a time, it becomes difficult to parallelize the training procedure. This becomes even more challenging when dealing with long sequences or large datasets.
Yes, and the recurrent connections in RNNs introduce a dependency on previous time steps, which means that each input needs to be processed sequentially. This hinders the training speed and efficiency, especially as the number of time steps increases.
Exactly. And as the gradients propagate through time, they may suffer from vanishing or exploding gradient problems, which further burden the training process. To address these challenges, researchers have proposed various techniques.
One approach is to use shortcuts to alleviate gradient vanishing or exploding. Another approach is to explore approximate inference methods. And there are also parallelization strategies being devised to expedite the training process.
Right. These techniques aim to make RNN training more efficient and less computationally demanding, allowing for their widespread application in various domains.
Absolutely. Moving on, let's talk about recursive neural networks, RNNs, and their potential in natural language processing, NLP tasks.
RNNs are capable of handling inputs with arbitrary sizes and structures, making them suitable for tasks involving syntactic and semantic analysis of sentences. They recursively apply a neural network to process the constituents of a sentence and aggregate the information at each level to generate a representation for the entire sentence.
This recursive nature allows RNNs to capture the hierarchical structure of sentences and dependencies between different words. As a result, RNNs have shown promising results in tasks such as sentiment analysis, part-of-speech tagging, and parsing, making them valuable tools in NLP.
Absolutely. And there have been several notable developments in the field of RNNs that hold great promise for future directions.
One significant advancement is the introduction of gated RNN models, such as the long short-term memory, LSTM, and gated recurrent unit, GRU, which effectively address the vanishing and exploding gradient problems.